that I found is the reinforcement learning is the learning what to do. That means how to map situations to actions so as to maximize a numerical reward signal. The learner is not told which actions to take, but instead must discover which actions yield the most reward by training them. And these definitions can be found in the reinforcement learning and introduction by one of the most famous reinforcement learning researcher, Sutton and Andrew. Now, what does it mean is that when we have the corresponding agent that is going through the reinforcement learning, that agent will not be told what to perform. Rather, it will perform the corresponding action, and based on the outcome, will provide the corresponding reward. And from that reward, the agent will understand how to improve, whether to improve or how to improve its corresponding parameters. Okay, but our topic of discussion will be the supervised learning, right? So let's focus on the supervised learning. There are two types of supervised learning algorithms. As I mentioned, in the supervised learning, we provide both the input and the output. Now, if the output is continuous, suppose I want to predict some house price prediction, right? The house prices are continuous data, numerical value. Okay. Now, if I want to based on the provided input data, training data, a model will be trained, the parameters will get its corresponding values, and eventually if we give some unknown house parameters, right, with the corresponding number of bedrooms or the carpet area and so on and on, it will be able to provide me the price of that house, the predicted price of the house. So in that sense, the data is continuous to be predicted, so it's a regression problem. Whereas the second one is a classification problem, where the data to predict is discrete, right? That means the output will belong to certain finite number of classes. As for the case of binary classification, uh, whether it is 0 or 1, right? As for example, whether certain tumor is malignant or benign, based on previous data, whether we can determine whenever we'll have the features of some new tumor, we'll be able to determine whether that is malignant or benign. It is either one or the other, right? Or we can also have multi-class classification, like the famous MNIST digit prediction. When we'll have the digits, which of the 10 classes it belongs to? The 10 classes, each corresponds to each of the individual digits from 0 to 9. Okay. Now SVM. Now first of all, let me tell you that among the regression algorithms, there are many regression algorithms available to us, like linear regression, polynomial regression. Polynomial regression is an extension of linear regression, and and some classification algorithms like the SVM itself can be used as regressor as well. But I'll come to that point later. Whereas among the classification, there are several algorithms like logistic regression or the SVM, which will be our today's topic, right? The support vector machine. So SVM is a classifier, right? So the output SVM it can also be used as a regressor as well, but it is mostly used as a classifier. So we'll focus on our study of SVM as a classifier as well. So let's enter the domain of support vector machine. How it performs the classification. First of all, before describing the support vector machine, let me tell you what is decision boundary in any classification algorithm. Suppose if we have been given data belonging to several different classes, okay, the classification algorithm will try to create a boundary, will try to draw a boundary so that the data belonging to different classes fall on different sides of the boundary. Okay, I'll explain it with an image in the next slide. What SVM does is that it tries to find the best hyperplane that will create the decision boundary. But what does it mean by best hyperplane? Suppose I have some data like this. We can say here, we can see here these are randomly generated are marked in blue, and some data are marked in the red color, and these two colors denote the two different classes, and our target is to find two dimension. We have to find a line which will be the decision boundary here. As I've said, decision boundary means the boundary where on the two opposite sides, the data belonging to the two opposite sides will belong to the different classes. So here you can see that we can create the decision boundary in many different ways, like the blue one or the black one, and we can draw many lines that will differentiate these two data quite perfectly. But which among these two, suppose I have these two lines, which among these two are better? First of all, what does it mean by being better? Both of them are dividing, right? The fact is, we will call that decision boundary as the best, which will separate the classes by the largest margin. As for example, we can see here from this blue line, the distance is okay, but the distance from the red class is quite lesser. Okay. Whereas if I balance it so that we can draw a line that will keep the largest distance from both of these classes. Okay. In that case, we will obtain this black line. In fact, this black line has been obtained by writing a real SVM code on this dataset. And this creates the best hyperplane. The hyperplane or the line that creates the largest distance from the corresponding classes. Okay. So here we come to our corresponding mathematical definition of our best hyperplane. So the equation of a line in 2 dimension, we can write that as, say, ax plus by plus c is equal to 0. Right. So what will be a target in 2 dimension? Target is to find the best line, and if we represent it in the vector notation like this, it will create the largest margin from the data points. In the 3 dimension, what we will receive is the best plane, right? And the class and the data sets on the opposite sides of the plane will represent the different classes. Okay. So and the equation of a plane in 3 dimension turns out to be like this: some ax plus by plus cz is equal to cz is equal to some constant is equal to d. But we have written it specifically in terms of w1, w2, w3 because we'll see now that these are the parameters that we need to modify. Okay, these are the parameters because these parameters define the corresponding line or plane or in much higher dimension hyperplane. So we have to modify these parameters to obtain the best hyperplane or the best line, right? So we have to train our data points in such a way that will obtain the best hyperplane. Now this is a generalized version. In the much higher version, suppose I have some n dimensional the data with n number of features. Okay, we'll have the n dimensional data in that case, and so the w, the weight, will also be n dimensional. So what we need to perform is the dot product of the corresponding weight vector, like we have done here, and the corresponding the basis vectors, right? Plus the basis is equal to 0, and it will create the largest margin. You have to find such hyperplane that will create the largest margin from the corresponding data points. Okay. So I started from 2 dimension, 3 dimension, and I've generalized it to the higher dimension. Okay, and this is the equation that we need to find. We need to find the best w that will the best weight vector w that will create this largest margin. Now, so this is that same data point. So this is the best line we can obtain. Now, if we go on the both sides and if we try to find the closest data point belonging to each of the two classes, these are the data points we'll see on the red side, and these are the data points we'll see on the blue side. Excuse me, I'm being able to hear some noise. It will be better if you kindly mute. Okay, so
FDP
we
join
have
parliament.
uh, so we have so we can see that these red points are the closest from this SVM hyperplane, and these blue points are closest from the corresponding hyperplane. Okay, now uh, the fact is the planes which will be parallel to this corresponding decision boundary and they will go to the closest data points of the two sides are called the support vectors. This is the name where it gets the support vector machine. So as for example, in this 2D case, these two lines drawn in magenta color are the support vectors. This is the support vector for the red class. This is the support vector for the blue class. We have to ensure that we have to train our model in such a way that the data points do not cross these support vectors. Okay, but that does not always happen. I'll come to that point, what to do in that case. So now we can take any equation. Obviously, if it is WTX plus B is equal to 0, this is the equation of this, as I've mentioned here. This is the equation of this hyperplane. So as these two are parallel to this hyperplane, there will be WTX plus B, some positive value for this line and some negative value for this line, right? Let me assume the value here is 1 and the value here is -1. We can take any value, but 1 and -1 eases the calculations of the SVM. Okay, so we are in fact restricting the data points to not appear further down the line WTX plus B is equal to 1 or -1. Okay. Now suppose the output will be +1 for the positive data points. So even if you have uh, even if you have mapped the data points, you have collected the data points with the positive values as 1 and negative values as 0, we can quite easily modify them. The positive value will remain as 1, but the negative value will become -1. And we are performing binary classification here. So the constant what we want is that the output data yi will be +1 in case the data points fall on this side of the decision boundary, right? So greater than is equal to 1, and it will be -1 if the data points fall on the other side of the decision boundary. So less than is equal to -1, right? Now, if we check this out, we'll see that in both cases where okay, xi is the corresponding yi is the output of the corresponding ith instance. So this should be true for every instance. This is one instance, this is one instance, and so on and on. And wtxi plus b will be greater than is equal to 1. Okay. So this is in fact the reason they are taken as 1 and -1. It eases the corresponding optimization constraint. So this is the constraint. We still have not discussed about what we need to optimize. I'll come to that point. But before coming to that point, I need to mention one thing, is that WTX plus B is this line. Okay. So WTX B is a constant, right? WTX for this line B is a constant. Eventually, this is also a parameter that we need to modify. But for a particular hyperplane in a particular direction, once you have obtained the direction is provided by this weight vector. Okay. For a particular direction, uh, this B will be constant, right? So suppose WTX plus B is the corresponding hyperplane. So WTX is equal to 0 will be a hyperplane parallel to this line. parallel to this plane, because because the weight vectors are remaining same and changing only the constant. So what we'll get is the parallel planes. Now if wtx is equal to 0, the dot product of w and x is 0. That means w is perpendicular to that plane there. That means weight vector is perpendicular to this hyperplane wtx is equal to 0, and as well as all the hyperplanes parallel to wtx is equal to 0. That means the weight vector, if we draw the weight vector, that will be perpendicular to this and these support vectors as well. Okay, so w is perpendicular to the hyperplane. Now we are going into a bit of linear algebra here. Suppose x1 is a data point. X1 and x2 are two corresponding representative data points of the two classes, and not only them, they belong to the corresponding support vectors. They lie on the corresponding support vectors. So x2 is the data point, one of the data points which lies closest to the decision boundary, and x1 is one of those data points which lie closest to the decision boundary from the other class. Now if we have these vectors x2 and we have these vectors x1, the vector joining x1 and x2 will be x2 minus x1. Okay. Now I have to, now luckily we can see that the x2 minus x1 vector is almost perpendicular to this support vector, but that does not always happen. This has created from when I wrote this code, this randomly generated points, they somehow turned out like this. But we can also connect this and this as well. In that case, obviously, if this point would not be there, we would connect this point, and we would not obtain a perpendicular to the corresponding support vector. But how will I get the shortest distance between them? Okay, how will I get the shortest distance between them? The shortest distance. So obviously, to get the shortest distance, what I have to do is that I have to obtain the directional component of this vector along the perpendicular w. W is the perpendicular. So along the perpendicular, you have to find the directional component of x2 minus x1, because that will give me the shortest distance between the two support vectors, right? And to obtain the directional, suppose I have a vector a, I want to get its component along vector b. Okay, and how to do that? Just perform the dot product of a and b. That means dot product of a and the unit vector in the direction of b, because I want to get the component of a in the direction of b. So that will be the dot product of a and the unit vector in the direction of b, right? So if I want to get the component of x2 minus x1 in direction of w, because w is a perpendicular to this hyperplane, so you'll get the shortest distance along this direction. So the shortest distance will be the x2 minus x1 and the dot product of the unit vector in the direction of w. So in unit vector in the direction of w is w by the vector w divided by its length, right? So w by the norm of w, and here we have the dot product of w and x2 minus x1 divided by the length of w, right? So this is the shortest distance between the two support vectors. Now our target is to find this direction. As I've said, the direction of these hyperplanes are decided by the weight vector w. So we have to find the direction in such a way that this distance will be maximized. What we have observed here, let's go back here, the distance, in fact, the direction in this direction of the blue line is not going to be maximized. But in the direction of this black line, it is going to be maximized. Okay, the distance, because when you will have this black line as the support, black line as the decision boundary, the support vector will be along this line, the parallel to this, and the distance between them is not higher, and this will be support vector here. And the distance between these two support vectors being parallel to this blue line will not be much higher. And so that's why the blue line is not the best hyperplane. Okay? Whereas, as you'll see, the distance of these two support vectors is going to be highest among all the possible directions you can imagine separating these two classes. So we have to find the W that will maximize this distance, the distance between the two support vectors. But let's look into the derivation here a bit. This is simple. I'm just taking the W to x2 minus W to x1. But if we observe here, the W to x2 plus B is equal to 1, because this is the support vector. We have assumed the W to x2 plus B is equal to 1. Okay. So W to x2 will be equal to 1 minus B, and W to x1 plus B is equal to minus 1. This one. W to x1 plus B is equal to minus 1, as you can see here. Okay. So W to x1 will be minus 1 minus B, and as I'm doing the minus here, all of them are going to be becoming plus, and eventually this is the term that you need to maximize, 2 by norm of W. So we have got our optimization problem. Here we have to maximize 2 by mod of W. So when it when we'll reverse this, when we'll take the reciprocal of this, that will become a minimization problem, right? So mod of W by 2. Now mod of W, the length of W means the dot product of W with itself, right? So we have to minimize the WTW by half, and this is the constraint that we have obtained here. So combining these two, this is the optimization problem that is in fact the SVM problem. Okay. So when we solve SVM, though the Python scikit-learn does this automatically, but when we perform SVM, this is the optimization problem that is being solved. But this optimization problem, but the question is how to, okay, before going to how to solve such optimization problem, let me come to the point of soft margin SVM. Okay. Here, let me come to this picture again. Here we see that the data are perfectly linearly separable, because when I created the random data, the creation code was made like this, so that the synthetic data will become perfectly linearly separable. But that's not always the case in reality. Some of the data, sometimes it will not even be separable linearly. I'll come to that point at the last when we'll study about the kernelized SVM. But in many other cases, these data points will not stay hardly, that means strictly, on its corresponding side of the decision boundary. That does not always happen in reality, in real data sets. So we have to soften the margin. Okay? That means we have to allow some data sets to appear within this support vector and decision boundary, as well as on more softer case, some data points can also appear on the other sides of the linear boundary as well, maybe one or two. But obviously you have to also make sure that not too much data points go on the other side of the decision boundary, right? Because in that case the meaning of decision boundaries does not make any sense. But just to make the margin softer, okay, to allow some instances to violate it, in that case we introduce another variable that's called the slack variable, that determines how much an instance, this slack variable will be for each instance. Okay, will be individual for each instance, and for a particular instance, a slack variable will determine how much an instance is allowed to violate the margin. But now at this point, we are down to two conflicting objectives. We have to minimize like this is our main goal. We have to minimize this, but at the same time we will also have to minimize the slack variables. Slack variables in the sense we have to minimize this because uh, so that not too many data points go on. That means too many data points start violating the decision boundary. So you have to minimize this as well. So uh, how can we merge two optimization problems into a single one? That's where the soft margin SVM's optimization problem comes in, and that's where the hyperparameter C comes in. Okay. Now the the optimization problem becomes the first target first goal plus some hyperparameter into the second goal. We have to minimize this as well as we have to minimize this as well. And at the same time, as we are allowing data points to go, that means break the boundary of of +1 and -1, as I mentioned there, that the support vector boundary, and this is the amount it is going to break, that boundary. So that's why it is being subtracted from 1. Okay. Originally it was yi to wtxi plus b greater than is equal to 1 in the hard margin SVM. But when we are softening the margin and we are allowing, say, ith instance to break the violation by the amount of xi, in that case, uh, we are subtracting that slack variable from 1. We are allowing that much amount of violence, that much amount of violation of the margin. Okay, we can allow only that much amount of violation of the corresponding margin. So now among these two uh, optimization targets, how the C parameter acts here? Let's see. As we have to minimize this complete expression now, if I start to increase the value of C, okay, in order to keep the uh, overall value minimum, the sum of the xi will try to reduce more and more, eventually reaching near to 0. As C limits infinite, the xi limits 0, making it a hard margin SVM. So as C increases, the hardness of the margin increases along with it. Okay, so that's how hyperparameter C comes into the picture of the SVM. When you write the SVM code, when you look into the SVM code, we'll see that we can control this C hyperparameter to uh, maintain the hardness or the corresponding softness of the margin. So this is the corresponding optimization problem in case of soft margin SVM. But how will I solve this optimization problem? Either hard margin or soft margin. I'll discuss it only for hard margin, because for soft margin the mathematics become much more dense. So to keep it simple, I'm going to uh, show just the steps of how to solve the optimization problem. I'll not go into the details of this because it will drift our discussion into a completely different channel. Okay, uh, those who are interested can study any good optimization books like Numerical Optimizations by Nosadal and Wright. So, but let me mention a brief about how these optimization problem can be solved in brief. Any constraint optimization problem. Okay, suppose I have any particular constraint optimization problem using Lagrange multiplier. In fact, if our constraints are limited to only equalities, okay, let me repeat it again. If our constraints are limited to only equalities, using only Lagrange multiplier is sufficient. Okay, But as soon as we start to have inequalities into the corresponding constraints, we also need to follow the Karish-Kuhn-Tucker conditions. Okay, I'll not go into the details of these, but eventually, by using these Lagrange multiplier and Karish-Kuhn-Tucker conditions, we can convert any constraint optimization problem into a dual problem. So that problem becomes this problem. For this alpha and alpha j, it looks much more a huge optimization problem to solve, but as you'll see, it is much easier to solve. Eventually, this alpha and alpha j, they are the corresponding Lagrange multipliers. Okay, and after converting it into the corresponding Lagrange multiplier form, we have to set the stationary points. That means of the corresponding equations, the partial differentiation of the corresponding equations with respect to the variables, all of them should be set to 0. And in that case, we get these conditions as well, along with this optimization condition. So for each data set, these conditions should also be followed as well. Here, we have to optimize these Lagrange multipliers. But the advantage of this format above this format, this format, is that this format is an advantage. This format is a pretty well-known structure of quadratic optimization. Okay, quadratic programming, right? So we can solve this optimization problem using any well-known quadratic programming solver, right? And after obtaining the quadratic programming solver, what you're going to get is the optimum value of these Lagrange multipliers. Okay, and after obtaining the optimum value, we can obtain the optimum value of the weight vector and the b using this. Okay, so this is the relationship between the Lagrange multipliers and the weight vector, and this will be the relation between the, in that case, once we have obtained the optimum weight vector, we can simply take any data point on one of the support vector of the positive support vector, where we will have the corresponding input data point and the output data point will be 1. If we can remember, in that case, wtx plus b equals equals plus 1. So in that case, b becomes 1 minus wtx. So this is what you can use to obtain the value, to obtain the optimum value of b. Okay. So that's the way we can solve the optimization problem. Now, now about the nonlinear support vector machine. Now, truth be told, in many cases, the data sets are not in fact linearly separable. Okay, and in such cases, we need to introduce some new features by combining the existing features. And that's exactly the same thing that is performed in all other machine learning algorithms. When we cannot solve, that is also done in the linear regression as well. When you have the particular number of features and we need to obtain the corresponding, we need to solve the polynomial regression. When it comes to the polynomial regression, we start to combine those features. Okay? As for example, if we have two features, say x1 and x2, this is not only true for linear SVM. In fact, it's true for any other machine learning algorithms that where the so here we have suppose the two features, the x1 and x2, and using linear SVM, what we'll do, we'll try to obtain the baseline as we have mentioned, the wn x1 plus wt x2 plus b is equal to 0. But what if we need a quadratic curve to separate the data points? We cannot separate those data points using a straight line. Rather, we need to obtain some quadratic curve, or the curve with that defined by some polynomial of degree 2. So in that case, we'll introduce 3 more features: x1 square, x2 square, and we'll start combining these features, x1, x2. What uh, if we want to obtain some, so if we need some polynomial of degree 3, some cubic polynomial to separate those features. Even quadratic curve is also not doing is not being able to divide those data points perfectly. So what to do in such case? In that case, if we have to resort to the cubic data points, cubic curve, the corresponding features that will become x1 cube, x2 cube, okay, x1 square, x2, x1, x2 square, like this, right? So now, so what we can say is that if we have suppose d number of features initially, and we need to obtain, say, polynomial, we need to separate the data points using a polynomial of degree m. What will happen is that we'll have to introduce we'll have to introduce number of new features in order of d to the power m. So that's some huge number of features that we need to introduce. And this is so we have to we can define a feature map. As for example, this x1, x2. So feature map, if you observe, this is a vector, the vector x, that is the original features, the vector of original features that we were using in the linear SVM. So x1, x2 were the original features, and we are going to uh, employ the feature map, okay, and we are going to obtain a vector with the 3 elements, x1 squared, x2 squared, x1, x2. So the feature map here is mapping a vector into another vector, mostly in a higher dimensional vector. So, but as I just mentioned, with higher number of features and the requirements of higher dimensional polynomial, the number of features to maintain becomes unmanageable. Okay. Suppose if we have say 10 features, or I'm taking only 10, but in reality we have some hundreds and millions of features, and we cannot fit on a straight line. We need to do, say, even with say 100 features, if we try to perform quadratic, if we try to find some quadratic polynomial, number of features is going to be huge. Okay. So in that case, the trick is to use the kernel function. Now, what is a kernel function? Let me go through this discussion very step by step. Kernel is a pretty special type of function. Okay. This will allow to compute the dot product of the mapped vectors phi a and phi b. That means suppose I have two vectors a and b, okay, and I have to compute the dot product of their mapped vectors. Okay. The idea of kernel function is that we can compute the dot product of these mapped vectors without computing this phi or phi b, and we can compute them only in terms of the original vectors a and b. So what is the advantage here, and how it can become advantageous for our SVM problem? To understand that, let's come back to this quadratic programming, or the corresponding the optimization problem that we need to solve. If we look into the complete equation, the data points are only having dot products among themselves. So eventually, when we will map these features to the higher dimensions, we'll also have to perform the corresponding the dot product of their corresponding mapped feature vectors, right? That means our SVM optimization problem involves only dot product of the feature vectors. And that's where the advantage of kernel comes in. If we can evaluate the dot product of the feature vectors without calculating all the features themselves, obviously it is going to increase the speed of the evaluation, right? So that's the trick. But how can we find how can we find such function? Here is an example of one such function. In fact, this is the quadratic kernel. Suppose this is the x1 and x2, this vector, and I have to map it to these three-dimensional feature vectors, x1 square, x2 square, and in the previous case we have used x1, x2. We are using root 2 x1, x2. That is doing the trick. Using only x1, x2 would not make it a kernel function. Now, let's perform the dot product of the corresponding the two vectors, say a is also a1, a2 like this, which will be mapped to a1 square, root 2 a1, a2 and a2 square, and b is also a vector with original vector as b1, b2, that is mapped by the by this feature map to b1 square, root 2 b1, b2 and b2 square. And if we perform their dot product, we are seeing that we are getting a1 b1 plus a2 b2 square. Eventually this is the dot product of a and b, the square of the dot product of a and b. So in the scenarios where we will have to evaluate the dot product of phi and phi b, phi a and phi b, we can altogether avoid evaluating phi and phi b. We can just take the dot product of a and b itself, which is computationally uh, faster than calculating the phi a and phi b. We can take the dot product of a and b and just take the square of that value, because as soon as you are taking the dot product, you are getting a scalar value. Just take the square of that and you are going to get the dot product of the corresponding feature maps without calculating them. Okay, so that's the advantage of kernel functions. And there are pretty common kernel functions that is used in the support vector machine. Like this is the linear kernel functions, which is used for the linear SVM, which is obvious. That means evaluating the dot product of the kernels of the corresponding kernel functions is equal to the dot product of the vectors themselves. This is the polynomial function. Here the gamma and the coef, the r is termed as the coef. I'll show that in the code. They are the corresponding hyperparameters that we need to control in the code if you are going to use some polynomial kernel. Okay. Then Gaussian RBF kernel. This is a pretty famous kernel, and this is the default kernel used in the SVM when we do not pass the kernel parameter in the SVM code. Okay, and this is the exponential kernel, as you can see, and then the sigmoid kernel. This is another pretty common kernel that is used in the nonlinear SVM. Okay, so all these kernels allow us to obtain. Now, once you have obtained these kernels, just use those kernels. Eventually, rather than using those kernels, obtain the corresponding representation in the own vectors like phi a t, phi b. What will be its format in terms of only a and b? Just put that here, and that will be the corresponding minimization function of the quadratic programming solver. Okay, that's the only difference. That's the only modification that you need to perform for the nonlinear SVM, and that is also the advantage of the kernel. We can directly put it here in this optimization problem. Okay. Now let's look into some real code. Okay. Here I'm going to load the IRIS dataset from the scikit-learn. Now, IRIS dataset is a dataset. It is a very small dataset. I'll show the first tutorial on this very small dataset just. Then I will apply these techniques on the amino acid DG dataset. Okay. So the iris dataset is a dataset of petals, the flower petals. Okay, and it is classified into three classes that will be printed here. But first, let me load that iris dataset. It is a small dataset with only 150 instances, and the key is in the iris dataset are these. Eventually, among them, this is the data. This is the main data that we are interested about. The target, okay, that contains the output, the y, that is known as the y, the target names. As this is a classification problem for y is equal to 0, what class it represents, a particular iris flower class. I is equal to 1, it represents a particular iris flower class, and I is equal to 2. In fact, the iris flower class is divided into three, contains three classes. Okay? And I is equal to 2, and the corresponding the y is equal to 2 contains another class of iris flowers. Okay. Uh, Now let me print them. First, let me look into this information. As you can see, the data has the shape of 150 and 4. What does it mean by 150 and 4? That means there are 150 instances, and each instance overall, the data set has 4 features. Okay? That means it is a 150 by 4 matrix. Right? And if we print the feature names, we can see that there are exactly 4 features: the sepal length, sepal width, petal length, and petal width. Right? Now the target names. There are 3 classes of flowers that I have mentioned: the Iris setosa, Iris versicolor, and Iris virginica. Now these are the target names provided into the corresponding Iris flower dataset. Now NumPy bean count, what it does is that it divides the corresponding output data, okay, into separate classes. Into that means like putting into separate beans. There is a bean for the class 0, there is a bean for class 1, there is a bean for class 2, and put each data, each output into the corresponding beans, and at the end it gives us a corresponding count of each bean. And as you can see that among the 150 flowers, the data set is equally divided among the 3 classes. There are 50 instances of setosa, 50 instances of versicolor, and 50 instances of virginica. Okay. Now, as I've said, we are going to keep it simple. So I'm going to take only the petal length and petal width. So I'm going to take the data column, the data field of the iris flowers, and I'm going to take the second column and the third column, okay, among all the rows. So this column represents all the rows. Among all the instances, I'm taking only the second column and the third column. That will be our X. That means I'm filtering out these first 2 columns. Okay. And Y, as I'm going to implement binary classifier. But if I keep only if I keep all these 3 classes, what we'll have is a multi-class classifier where I have to divide the instances into multiple classes. But to keep it simple, I'm going to perform a binary classifier. That means determining whether a particular flower belongs to class 2, that means belongs to class virginica or not. Okay. And if I execute this, again, you'll see that as I filtered out 2 columns, now I have 150 instances of 2 columns left, petal length and petal width, and the wider shape is of size 150. In fact, these 150 are now only 0 and 1. In the original data set, those output which were 2 in the original data set, in the Y data set now they are 1, and which were not 2, they are now 0. Okay, so it is now 0 or 1, either 2, that means either it belongs to the iris virginica or not, in which case it is 0. Now I'm going to, it is a very small data set. So, but still it is a, I just, it was not necessary to divide this into training and testing data set, but still to keep with the best practices, I've divided it into the training and testing data set with 75%. 112 is around 75% of 150. So first 112 features, 112 instances are going to the training, and the left data set are going to the testing data set. Similarly, I am taking the first 112 for the training, and after the first 112, the rest of the data set output in the testing. And then I'm going to create a SVM classifier, and I'm going to put it into a pipeline. So via the pipeline, it will first have to go through a standard scaler, and then it will go via the linear support vector classifier, linear SVC. Okay. Now, what the standard scaler does? Standard scaler, it takes the complete data set, and it uh, it scales the data set in such a way that the mean of the final data set will become 0 and standard deviation will become 1. Okay. So the standard scaler does that scaling of the corresponding data set. And then I'll have the linear support vector classifier. I'm putting a very low value of C. That means I'm keeping a pretty soft margin. Okay, and I'm using the hinge loss. And if then I'm going to put the X train and Y train, the shape of this, and then I'm going to fit the corresponding X train and Y train to the corresponding classifier. So after this fit function, the classifier will train itself to best fit the corresponding to best fit its parameters by solving the corresponding optimization problem to best fit its parameters, the weight vector and the bias vector B, to so that the Y train uh, becomes a perfect matching function from the corresponding X train instances. So it was pretty fast because we did not have much amount of data to train. Now I'm going to perform. That is how the performance measures of a classifier is generally performed. I'm not showing the confusion matrix and so on here, just to keep it simple. I'm going to use the cross validation score on the X train and Y train dataset, right?
Sir, could
And
you just repeat that standard scalar once again?
Excuse me.
Standard scalar, that
Okay.
point.
Standard scalar, it maps the data set into the data set with mean 0 and standard deviation 1. If we go on to this, and you can see here, standardize the features by removing the mean. That means the mean becomes 0, and scaling to unit variance. Variance 1, that means standard deviation. Then standard deviation 1. Okay. So even if we have a very varying data set, that means the data sets containing various types of features in a various types of data in it, all of them will be scaled to the corresponding data set with this in the range of 0 mean and the standard deviation 1. Okay, that's the task of standard scalar. That makes the
Right.
the training of the classifier easy. Okay, thank you. So what it is going to do now, you can see that among the training data sets, the cross validation scores are pretty well, but that's obvious because we have trained it on the training data set. Now on the testing data set, what I'm doing here is that I'm performing a stratified split. Stratified split means it is going to be split into 3 parts. These 3, it does not match with the 3 classes. I'm going to part in three parts, and the data will be shuffled completely, and it will split it in such a way that from each class, doesn't matter how many classes are there. In this case, I have only, doing original problem, I had 3 classes, but I have mapped here to the 2 classes. So doesn't matter how many classes we have here. But from each class, after the split, from each class, the number of instances will be equal in the corresponding folds. The advantage of this is that in here we have simply taken the X test as a blindly from the first 112 and X train from the first 112 and X test from the last 112. But that does not necessarily mean that in last few instances the classes are in equal proportion, right? So to make the to understand the performance of my classifier, I'm separating, I'm telling, I'm performing it a stratified split. So they will be classified into the folds into with equal proportion. Okay, so it is going to take each index from the training data set and the so from it will take the X train and Y train, it will perform a split and it will create one training index, which of the instance will go to the train and which of the instance go to the test. Okay, then I'm taking this corresponding X train and Y train, the corresponding uh, and then the corresponding testing instance and the testing output. So X train fold is that after the performing the split, X train fold is the input of the instance that is going to the training side, and Y train fold is the output of the instance going to the training side. Similarly, X test fold is the input of the instance going to the testing side, and similarly is the output of the instance going to the testing side. Okay, and then it will it will it will fit that classifier into this train fold, because now we know that the folds has been done in equal proportions. Okay, so the performance measure that you are going to see now are quite valid measures. Okay, but as during the fit its parameters will modify themselves. So what we have done is that before performing this fit we have cloned our original SVM, and then we are fitting the parameters, we are updating the parameters of the cloned classifier rather than on the original classifier, because during this fit the parameters are going to modify themselves. Then I'm going to perform the prediction of the corresponding testing fold, and then the way we perform the corresponding how many percentage of our testing fold has come as true. So it will check how many of them are corrected. So for all those instances where the predicted value is same as the corresponding value of the testing output fold, all of them will be summed up. So eventually this sum will contain exactly the number of instances in the corresponding testing fold where the prediction has appeared to be correct. Okay, so then just divide the length of the prediction, that means the length of the overall testing fold. In fact, divide the corresponding number of corrects outputs by the overall length. That's usual. So this is going to give me quite accurate prediction of my model. Okay, and as you can see, the model has performed pretty good among the three folds, among the three splits. Uh, these are the this is the performance in the three splits that you can see. Eventually, when we will provide the corresponding final accuracy, we can provide their average. By default, the number of splits is 5. That means it performs the 5 splits of the overall dataset. In splits is by default 5. Okay, so that was a pretty simple example. Now, because our dataset was very small, now we are going to perform the same uh, on the real immunized dataset. But before that, excuse me, I'll take a a small,
3 minutes.
a few seconds break.
PBT, okay, you have recently joined the paper. Then, actually, so you are not getting the answers.
We are not getting
Daily
access.
basis.
Daily
Anytime answers. Okay, once you text to set up payment, like your name, your roll number.
And for me, Meritco is not open, showing in
Unmute yourself.
Okay.
Please
Now,
continue.
yeah, thank you. Now we are going to perform those same operations on the MNIST dataset. Here we are fetching the MNIST dataset using the fetch OpenML function. And again, it has the corresponding keys that we have exactly seen for the case of iris dataset as well. And in the MNIST data, there are 70,000 digit informations, digit images. Each digit image is in fact 28 cross 28 image. So 28 cross 28. So overall, there are 784 pixels for each image. Okay. So the data is have 70,000 rows, and each row has 784 pixels. Each pixel will be the deciding factor in evaluating the corresponding parameters. So each of these 74 pixels will be the corresponding features. Okay. And there will be 70,000 information into the Y. But this Y now has 10 classes from starting from 0 to 9. Again, I'm going to perform binary classification. In fact, multi-class classification is time consuming, but that can be just be performed as an extension of the binary classification by taking each class separately. As for example, I'm going to first take the class 1. Those instances which belong to class 1 will put as 1, and all the other classes as class 0. Then we'll perform the classification, and we'll check which instances belong to class 1. Okay. Then we'll continue this for the class 2, class 3, and so on. That is one technique. But obviously, for neural for this image datasets, 7SC image datasets, neural networks work great with the corresponding 10 neurons in the output layer, but that is out of the scope of this discussion. So, so what I'm going to do here is that I'm going to just as a test, I'm going to print the first digit of my input data set, and that's 5. And it also prints 5 from the output information. Now, the customary is to divide. If we're going to use the mnis.load data in the TensorFlow's Keras, but it will automatically divide it into 60,000 and 10,000 training dataset and testing dataset. But as we are not going to the TensorFlow here, we are going to divide it manually. Okay, and what we're going to take is that the first 60,000 as a training dataset and the testing, and the last 10,000 as the testing dataset. Okay, and again I'm going to convert it into a binary classifier, as I mentioned. And here I'm looking 5 here, so I know that in the training dataset there is at least one 5. So I'm going to separate on the corresponding train 5. Okay. So y train 5 will now have the binary output with zeros in those cases where the training value is not 5. That means the output is not 5, and 1 in those cases where the output is 5. Similarly, I am converting the testing dataset into a binary dataset based on whether it is 5 or not as well. And then I'm printing the corresponding X train and Y train shape, and they are going to give me the obvious output. Then I'm going to use the linear support vector classifier. I'm using linear here with the softening hyperparameter set to 10. But even with this much amount of softening the margin, it is not very high value of C. In fact, you can see here the in fact this linear SVC will even fail to converge. Okay, and once it is failed to converge, there is no point of running this. But still, let me execute it again. And if it fails to converge, there is another thing we can do, is that we can increase the number of iterations. That's a common trick in such cases. And let's see if it converges in such case, but it is going to take some huge amount of time for that. So by the time it gets trained, the rest of the part is exactly the same as the tutorial one. Okay, in fact, this is the technique of using support vector classifier, but only the linear support vector classifier. I'm not going to save it. So there is another way we can define linear support vector classifier, is using the SVC function itself. And that SVC function is also belong to this sklearn.svm class, and passing the kernel as linear. That also performs the same thing. This is this linear kernel, right? And then C equals 10, etc., and so on and on. What we are mentioning here, it will perform the same thing. So using linear SVC and using SVC with kernel is equal to linear is the same thing. They are both of them are going to perform the same thing. So let me remove this and come back to our main code. I have shown this because by the time it gets trained, let me look into some other kernels. It's also in the same way, in exactly the same technique. We have fetched the MNIST data, and all of them are same. The only difference here is that I am using the polynomial kernel with degree 2. Okay, polynomial kernel with degree 2 and the coefficient value of 1. Gamma, let me come to this polynomial kernel. This coefficient value of 1 and the gamma will be taken as auto, but we can set gamma here as well. We can set certain value of gamma, but that's not necessary here. Okay. We will see setting this gamma in the corresponding Gaussian RBF, because we do not have any another hyperparameter like R here. So we have to control it via setting gamma only. Now, if we use this again, we can see that exactly like we can perform even with just by the time we come here, even with 10,000 iterations, it failed to converge. Okay, so after that we can look into the output, the corresponding on the corresponding 3 folds of the training data set and 3 folds on the corresponding training and testing data set with the stratified division. But truth to be told, these outputs do not make any sense, because overall this model has even failed to converge. The linear model will not converge in this case, because MNIST digit is a bit complex for a linear model. Okay, so let me come back to the polynomial model, polynomial kernel SVC with degree 2, and here I'm setting the coefficient value of 1, and again I'm setting the margin hyperparameter to 5, and then it has been trained. It took some huge amount of time to train, so I'm keeping this output here. Now after, so I'm not retraining it, because it is going to take some huge amount of time. But we can see here it has not failed to converge. It has converged successfully. So the digit data set between those which are 5, which are not 5, they can be separated by a polynomial curve. This is what it proves. Okay, and the performance is not bad. The corresponding cross validation score for the three classes is pretty high. Okay? And when we performed the stratified division with the 3 folds, the corresponding performance is also pretty high as well. So it is giving me pretty good performance. But why it is not being used then? First of all, it is not multi-class classifier. It is binary classifier. I've converted it into a binary classifier. Okay. Even on the binary classifier, it is going to take a huge amount of time. Now, if I am going to test it on 10 different classes, okay, it will give me a good model, but at the cost of huge, but with much larger cost. Okay. At the same time, a simple neural network will give me pretty good performance and pretty fast. Okay, and that is the reason that for such MNIST digit data, deep neural networks or the convolutional neural networks are being used majorly. Okay, so that's about how to use a polynomial kernel. And in the same way, we can use a Gaussian RBF kernel. Right? We can run them in the similar way as well. And truth to be told, at least on the laptop from which I am showing this presentation, the RBF kernels could not end this training. It took so huge amount of time. Okay? With this gamma value of 5 and C value of with so much software margin, even with so much software margin of 0.001, it could not finish in. I had to hard stop it. Okay, so I'm not going to execute it, but this is just a demo to show how to use the various types of kernel. And we can see that for the kernel parameters, we have the linear, as we have seen, that will give me the linear kernel support vector machine, the polynomial support vector machine. RBF is the Gaussian RBF, sigmoid, and if we wish, we can use some pre-computed kernel as well, but that is a much more general sense out of SVM, that we can use a pre-computed kernel in such cases, and will be out of the course for this discussion, because all those algorithms which accept some pre-computed kernel, all of them work in the same scenario. So that's how we can use RBF. Okay, there's no point of running this code. The output of this will be the same like what we have seen in the previous case. But if we run this code, it's not going to end in any pretty reasonable amount of time. Okay, so that's our discussion about how the SVM works, the background mathematics, how we can solve the optimization problem of SVM, and how to use SVM in real applications. So support vector machine is an excellent choice for classification problem. Okay, as long as we are staying within machine learning and not going into the deep learning regime, so SVM is a pretty good choice. Isn't this pretty powerful? Okay, and the softness of this margin can be regulated by the C hyperparameter that you have seen, which need to be tuned properly to obtain better classification result. Okay, generally we'll start with much harder margin, so that the violation, that means higher value of C, so that the violation does not happen much. But if we are not getting better performance, we'll start reducing the value of C to allow more and more instances to violate the margin and so on. And again, if the problem is not linearly separable, as you've seen, there are various kernels that can be used. So thank you. I'm open to questions. Still running?
Thank you, sir. So, dear participant, I just share one very small assessment link in the chat box related to today's class. Please try to submit it. And if any of you having any questions, you can ask to chat box also, no problem.
Thank you, sir, for your wonderful contribution for this sport vector machines. And I think all of the participants have uh, a good knowledge from this session. You have very well explained the basic background of machine learning and how the things are being partitioned into different types like supervised, unsupervised, semi-supervised, and reinforcement learning. And then you have very good explained the basic mathematics behind the support vector machines and how a better hyperplane is being able to find the decision boundary, how to get the best hyperplane and solve the optimization problem. And uh, literally you have well explained all the on two data sets how we can use the SVM using different classifiers, using different kernels. So it's a very good efforts from your side, sir. Thank you so much, sir, for your valuable time and valuable information as well.
Thank you.
So, dear participants, if you have any queries regarding today's session, you can ask, free to ask, please. Yes, sir. Sir, there is a one question from Dr. N. Bhopal.
Okay.
He said that please explain semi-supervised learning where it is used.
Generally, when we obtain data sets, what happens is that suppose you have a generally huge amount of data sets are generated, and those data sets are labeled manually in majority of the cases. And in scenarios when those data sets are labeled manually, obviously it is not possible to label all the data sets by hand. Okay, so in such cases, what is done is that at least from each of the classes, some of the data sets are labeled and rest of the data sets are left unlabeled. And the semi-supervised algorithm, they use those labeled data sets to train themselves to identify, to in fact find the pattern that the corresponding unlabeled data sets for any particular unlabeled data set to which class of the labeled data sets is belong closest. This is just a simple example. And it tries to label that corresponding unlabeled data in that way. And in this way, it tries to increase its own performance.
Okay, sir. Thank you, sir. Sir, there is one another question that why can we choose SVM over deep learning by Mr. Vivek Thapa?
Truth to be told, where deep learning or the neural network can be used, neural network is much preferred over the SVM in such cases. Okay, so there may be some few scenarios for very simple problems where the designing of a network is not much required. In such scenarios, the machine learning classifiers like logistic regression or SVM can be used. But for complex classification problem, I always suggest to go for deep learning to design a proper deep neural network.
Sir, is there any way to be distinguished between over the dataset whether the dataset is of image image type or whether the data set is of numeric type? Is there any relation like when we are going to opt for SVM or deep learning programs?
I think in such scenario that depends on the problem, and when we try to solve a particular problem, we already have the data set on our hand. When we try to train a particular model on our data set, we ourselves first look into the data set manually, right? And based on that particular data set, and from that we get to know that whether it is an image or some textual data or some simple numerical data, and we decide our algorithm based on that. For if we have some image, we'll first check, we'll first see, we in majority of the cases we'll go for CNN in that case. If you have some textual data, we'll check for RNN or NLP in such cases, and so on and on. So we first look into the data set ourselves, and based on that we take
Okay,
the
sir.
decision.
Okay, sir. Okay, sir. Thank you, sir. Thank you. Fine. Yes, any other questions from the participant side, please? So, sir, I think there is any other query from our participant sides. So, once again, sir, we would like to thank you for your valuable time, and hope we will also invite you in the future if we are going to having such. Thank you, sir, for your valuable time again.
Thank you very much.
Thank you, sir. Thank you.
Yeah. Thank you.
So all the participants are requested that feedback form link is being shared. So please give us the feedback for this session also. So today we end up with our fourth day of FTP program. So we are having a wonderful session by Dr. Mayuk Sarkar. So hope everybody of you have learned a lot from this session. So on Friday, I mean to say tomorrow, so we are having a session on mechanism design for resource allocation, and the speaker for today, tomorrow will be the Dr. Garima Shakya from Koshu University, Japan. So timings will be the same from 1:30 p.m. So all of you are requested to please join the FDP program sharp at 1:30. So once again, thank you for all the participants. Thank you for joining us. Thank you.
are you doing? Yeah, the one who's starting and says exam.
Anyone please kindly share the feedback from because